Right now, wherever you are, everything probably feels still. Perhaps you're lying in bed, listening in the dark. The walls around you are quiet. The floor beneath you feels solid. Outside, the night may seem almost motionless. But nothing around you is truly still. The earth is turning beneath your room. At the same time, it is carrying you around the sun at tens of thousands of miles per hour. The sun is moving through the Milky Way, and the Milky Way itself is traveling with dozens of neighboring galaxies through a much larger cosmic landscape. And somewhere inside that landscape, something appears to be missing. Not stars, not light, but matter. Astronomers mapping the nearby universe have found evidence that our galaxy may lie inside an enormous underdense region, a place containing fewer galaxies and less matter than the cosmic average. Its exact size is still debated, but some estimates suggest it may extend for hundreds of millions of light-years around us. You cannot see its edge. There is no glowing boundary in the sky. No dark circle surrounds the Milky Way. And this is not a black hole. Nothing is waiting to drag us inward. Light moves through this region freely, and countless galaxies still shine inside it. The hole is not an object. It is a vast cosmic valley. Imagine rising slowly above the Earth, leaving the planets behind, then traveling beyond the spiral arms of the Milky Way. Our galaxy would shrink into a pale island of stars. The local group would become a small gathering of lights. Farther out, galaxies would begin to arrange themselves into long threads and walls, while broad regions between them appeared strangely thin. Our home may lie inside one of those thin regions. Scientists sometimes call it the local hole, the local underdensity, or the KBC Void. These names do not always describe one perfectly round structure. The true shape may be uneven, with shallow and deep areas spreading in different directions. Researchers still disagree about where its boundaries lie, how much matter is missing, and whether the Milky Way sits near the center or simply somewhere inside a much larger depression. That uncertainty does not make the mystery weaker, it makes it more honest. We are looking at a structure too large to view from the outside, trying to reconstruct its shape while living somewhere within it. Yet the possibility itself is remarkable. Every human being who has ever looked into the night sky may have done so from inside an unusually empty part of the universe. And that emptiness may still be growing. Cosmic voids are not frozen cavities. Over billions of years, gravity pulls matter toward denser regions. Galaxies drift toward distant walls and filaments. The interiors of voids become thinner, while their boundaries slowly move outward. The void does not grow by swallowing the universe. It grows because matter continues to leave it. Nothing about this process threatens the Earth. It cannot tear apart the solar system or suddenly darken the sky. On human scales, it is far too slow and far too distant to feel. But on cosmic scales, the neighborhood around us is still changing. Galaxies are moving. Matter is gathering elsewhere. The empty regions between the great structures of the universe are becoming wider and deeper. And because every measurement we make begins from this one location, our cosmic address may influence what we think we know about the universe beyond it. It could slightly affect how fast nearby galaxies appear to move away. It may contribute to a disagreement over the expansion rate of the universe. Or it may simply reveal that our surroundings are more complicated than the earliest maps suggested. To understand any of this, we first have to let go of a familiar image. The universe is not an endless sea of galaxies scattered evenly through the dark. It has structure. Galaxies gather into clusters. Clusters connect through enormous filaments. Between those glowing threads lie vast regions of near emptiness. And before we can understand the whole around us, we must first see the hidden web that surrounds it. For a long time, the universe was easy to imagine. Stars filled the sky. Galaxies floated beyond them. And between those galaxies stretched an endless darkness, like a black ocean scattered with islands of light. But that picture is wrong. Galaxies are not spread evenly through space. They gather into groups, clusters, walls, and immense chains extending for hundreds of millions of light-years. Between those structures lie regions where very little matter remains. Seen from far enough away, the universe does not resemble a sea. It resembles a web. Imagine leaving the Milky Way and traveling outward until our spiral galaxy becomes only one faint point among many. Nearby galaxies begin to collect into small families. Those families gather into clusters. The clusters align along long, glowing threads, and the farther you travel, the more clearly those threads connect. At their intersections sit enormous concentrations of matter, places where thousands of galaxies can gather within the same cosmic neighborhood. These are the dense nodes of the web. Between them stretch filaments, vast bridges made of galaxies, gas, and dark matter. Some are so long that light would need hundreds of millions of years to travel from one end to the other. And between the filaments are the voids. These are not small gaps. They are enormous regions containing far fewer galaxies than average. A spacecraft traveling at the speed of light could cross one for millions of years and still see only a sparse collection of galaxies scattered through the darkness. Together, these structures form what astronomers call the cosmic web. It is one of the largest patterns known to exist. The web is not something telescopes see in a single photograph. No instrument can stand outside the universe and take a picture of its entire shape. Instead, astronomers build it piece by piece. They measure the positions of galaxies across the sky. They estimate their distances. They compare their motions. Then they place each galaxy onto a three-dimensional map. As those maps grow, the same pattern appears again and again. Dense clusters sit at intersections. Filaments connect them. Walls stretch between neighboring regions, and voids fill most of the space in between. This does not mean the universe is disorganized. The cosmic web is the result of order emerging from very small differences that existed long ago. It also does not mean the cosmological principle is broken. That principle does not claim every region must contain the same number of galaxies. A galaxy cluster can be thousands of times denser than the interior of a void. Instead, it says that when the universe is viewed on a large enough scale, no direction or location should be fundamentally preferred. Smaller structures may be uneven, but the larger statistical picture should remain broadly consistent. Voids are therefore not mistakes in the universe. They are part of its structure. They are as natural to the cosmic web as the empty spaces between the threads of a spider's web. Without them, the dense structures around them would not have taken the shapes they did. This changes the way we should think about emptiness. A void is not simply leftover space. It is a region with a history. Its shape reflects where matter moved, where gravity pulled most strongly, and how the universe evolved over billions of years. The galaxies along a void's edge did not appear there by accident. Many were drawn toward denser surroundings over immense periods of time. Matter collected along the boundaries while the interior became thinner. In this way, the web and the voids grew together. The denser parts became denser. The emptier parts became emptier, and the contrast between them slowly increased. Our galaxy sits within this architecture, surrounded by structures such as the local group, the Virgo cluster, and the broad region often called Laniakea. But even these are only small pieces of the full web. From a great enough distance, the Milky Way would vanish into one filament among countless others. The local group would become almost invisible. Entire superclusters would shrink into faint knots, connected by threads of matter. Only the voids would remain obvious, not because they shine, but because so little shines inside them. And this is where our story becomes personal. Evidence for a local underdensity suggests that the Milky Way may not sit along one of the richest parts of the web. We may live in a broad cosmic valley, where galaxies are more widely separated and matter is spread more thinly than in denser regions beyond. That does not make Earth the center of anything. It does not make our location chosen. But it may make our viewpoint unusual enough to matter. Every telescope looks outward from this place. Every map begins here. Every measurement of nearby cosmic expansion is influenced, at least slightly, by the distribution of matter around us. To understand why that distribution became so uneven, we have to travel farther back than the first galaxies, farther back than the first stars, back to a time when the universe was almost perfectly smooth, and the great emptiness around us existed only as a tiny imperfection. Long before there were galaxies, before the first stars ignited, the universe looked almost perfectly smooth. Almost. In the first moments after the Big Bang, matter and energy filled space in a hot, dense state. There were no planets, no stars, no black holes, and no empty regions wide enough to notice. Yet even then, the universe was not completely uniform. Tiny differences already existed. Some regions contained slightly more matter than others. Some contained slightly less. The differences were tiny, but gravity is patient. A region with slightly more matter created a slightly stronger gravitational pull. That pull drew in a little more material. As more matter arrived, gravity grew stronger, attracting even more. The process fed itself. Over billions of years, denser regions became places where gas gathered, stars formed, and galaxies assembled. Those galaxies collected into clusters linked by long filaments, building the cosmic web. But while matter flowed toward those growing structures, it had to leave somewhere else. That is how a void begins. A region that started with only a little less matter than average became increasingly empty as gravity pulled its contents toward denser surroundings. The difference deepened slowly. The interior became thinner. Matter gathered along the edges. A cosmic void is therefore not a place where nothing ever existed. It is a place from which matter gradually departed. Imagine following one small patch of the early universe. At first, it differs very little from the regions around it. It still contains gas, dark matter, and the seeds of future galaxies. But beyond it lie slightly denser areas. Their gravity pulls more strongly. Particles begin drifting outward. Gas follows. Dark matter moves too, even though it cannot be seen directly. Over time, more material leaves the central region than returns. The emptiness grows. The galaxies that do form inside such a region are often more isolated. Many lie near the edges, where the supply of matter is greater. Others remain scattered through the interior, separated by distances that continue to widen. As the void expands, its boundary becomes more important. Matter does not simply vanish. It collects in the surrounding walls and filaments, helping make those structures denser and more sharply defined. In this way, the bright parts of the cosmic web and the dark spaces between them are connected. The web grows because the voids deepen. The voids deepen because the web gathers matter. Each shapes the other. This process occurred across the observable universe, wherever small variations in density were present. Some underdense regions remained small. Others expanded into larger cavities, and when neighboring voids grew, the thin boundaries between them could weaken, allowing smaller regions to merge. Astronomers sometimes describe this as a void hierarchy. A small void may exist inside a broader underdense region. Several neighboring voids may join over time. The result is not always a perfect sphere, but a complicated landscape of hollows, ridges, and connecting channels. Some voids grow quietly for billions of years. Others do not survive. If a small, underdense region lies inside a much larger, denser environment, the surrounding gravity can compress it. Its boundary may collapse inward as nearby matter overwhelms it. So, even emptiness has different possible futures. Some voids are squeezed away. Others expand and merge. The largest become dominant features of the universe's structure. This helps explain why cosmic voids often appear irregular. They are not bubbles blown into space from a single center. They are the result of countless gravitational interactions unfolding across time. Their shapes remember where the matter went. A narrow channel may reveal where two underdense regions began to connect. A dense wall may mark the place where matter from opposite sides accumulated. A chain of galaxies along the boundary may trace billions of years of slow gravitational movement. To us, the universe can appear frozen. A photograph of a galaxy cluster shows no visible motion. A map of the cosmic web seems like a still image. But that stillness is an illusion created by our short lives. On cosmic timescales, the structure is flowing. Galaxies move toward clusters. Gas streams along filaments. Dark matter gathers into vast invisible frameworks. And voids continue to open between them. The process is too slow for any human to watch directly. But compare the universe today with the universe billions of years ago, and the transformation is dramatic. The early cosmos was smoother. Its filaments were thinner. Its clusters were smaller. Its voids were shallower. As time passed, gravity amplified the original imperfections. The dense regions became crowded with galaxies. The underdense regions became enormous oceans of near emptiness. And somewhere inside one of those oceans, or near the bottom of a broad cosmic valley, the Milky Way eventually formed. This means the emptiness around us is older than Earth, older than the Sun, older than the Milky Way itself. Its story began before the first starlight crossed the universe. If the local underdensity extends as far as some observations suggest, it may be the mature result of an imbalance born in the universe's earliest chapters. A difference too small for any eye to notice became a structure large enough to surround entire superclusters. That is the power of gravity acting over deep time. It can turn a slight excess into a mountain of galaxies. And it can turn a slight absence into a void hundreds of millions of light-years wide. If matter has been draining from cosmic voids for billions of years, then the emptiness around us should have left evidence. The question is how to find a hole that has no surface, no color, and no edge we can see. A cosmic void cannot be photographed the way we photograph a planet. It has no surface to reflect light, no atmosphere, no glowing edge. If you pointed a telescope toward one, you would not see a dark circle cut into the sky. You would simply see fewer galaxies. That absence is the first clue. Astronomers began mapping the large-scale universe by doing something that sounds almost ordinary. They counted. They divided the sky into regions, recorded the galaxies they could detect, and compared one direction with another. If matter were distributed evenly on sufficiently large scales, then similar volumes of space should contain roughly similar numbers of galaxies. But some regions repeatedly came back thin. A few missing galaxies could be blamed on chance. A larger gap might result from dust, limited telescope sensitivity, or galaxies too faint to detect. But when the same underdense pattern appears across different surveys, different wavelengths, and different observing methods, the absence becomes difficult to ignore. Still, counting galaxies on a flat image is not enough. The night sky hides distance. A bright galaxy may be relatively nearby. A faint one may be much farther away. Two galaxies appearing side by side in the same photograph may actually be separated by hundreds of millions of light-years. To reveal the true structure of space, astronomers need depth. They obtain it by studying light. As the universe expands, light traveling through it is stretched. Its wavelengths become longer, shifting toward the red end of the spectrum. This is known as redshift. The greater the redshift, the farther away a galaxy generally is, although local motion can slightly complicate the picture. By measuring this stretching, astronomers estimate the distance to thousands, then millions of galaxies. Each one becomes a point on a three-dimensional map. At first, those points may seem scattered. Then the structure appears. Long filaments of galaxies emerge from the data. Dense clusters form at their intersections. Broad walls stretch across space, and between them are empty-looking cavities, voids. These maps are among the closest things humanity has to an aerial view of the cosmic web. But even they do not provide a perfect answer. The boundary of a void is rarely sharp. There is no line where normal space ends and emptiness begins. Galaxy density simply decreases, sometimes gradually, sometimes unevenly. One side may be deeper than another. A smaller void may open into a larger one. Thin filaments may cross the interior. This makes the word hole useful for imagination, but imperfect for science. A cosmic void is more like a valley than a tunnel. Its edges rise slowly. Its center may not be obvious, and when you live somewhere inside it, even the direction of the slope can be difficult to determine. Galaxy counts reveal where visible matter appears to be missing, but visible matter is only part of the story. Much of the universe's mass does not shine. Dark matter cannot be seen directly, yet its gravity influences galaxies, gas, and light. A region containing fewer luminous galaxies may also contain less total matter, but the relationship is not always simple. Some galaxies shine more brightly than others. Some remain hidden behind dust. Some surveys are better at detecting certain kinds of galaxies. So astronomers must compare many forms of evidence. One powerful clue comes from motion. The universe is expanding, carrying distant galaxies away from one another. But galaxies also have smaller local movements caused by gravity. These additional movements are called peculiar velocities. A galaxy near a massive cluster may be pulled toward it. A galaxy inside an underdense region may drift away from the emptier interior and toward denser structures beyond. By measuring both distance and motion, astronomers can reconstruct something the eye cannot see: the gravitational landscape. Imagine placing a collection of leaves on a slow-moving river. You cannot see the shape of the riverbed beneath the water, but by watching how the leaves drift, accelerate, and change direction, you can infer where the currents are strongest. Galaxies reveal the hidden distribution of matter in a similar way. Their motion tells us where gravity is pulling. And where gravity pulls weakly, an underdensity may be present. Another clue comes from the light of more distant objects. As light crosses the universe, its path can be bent slightly by gravity. This effect, called gravitational lensing, allows astronomers to map matter whether it shines or not. Dense regions bend light more strongly. Underdense regions leave a weaker lensing signal. When galaxy counts, redshift maps, peculiar velocities, and gravitational lensing all point toward the same broad pattern, confidence grows. But uncertainty remains. Different surveys do not always cover the same portion of the sky. The Milky Way itself blocks our view in certain directions. Dust and stars within our galaxy create a difficult region, sometimes called the zone of avoidance. It is like trying to map an enormous landscape while standing inside a forest, with part of the horizon hidden behind the trees. This is one reason estimates of our local underdensity vary. Some studies suggest a broad region extending hundreds of millions of light years. Others find smaller structures nested within a more complicated pattern. Some measurements indicate a modest shortage of matter. Others suggest a deeper deficit. The disagreement does not mean nothing is there. It means the structure may be more irregular than the simple image of a giant sphere. We may be living inside overlapping valleys rather than one perfect whole. And because we cannot step outside the universe to look back, every map must be constructed from within the very structure we are trying to understand. This is the strange difficulty of cosmic cartography. Astronomers search for something invisible by counting what is absent. They trace darkness using light. They map gravity by watching galaxies drift. And when those galaxies are placed in 3 dimensions around the Milky Way, our location begins to look increasingly unusual. Not central to the universe, not uniquely important, but perhaps less average than we once assumed, and that possibility leads us toward our true cosmic address, a broad, underdense neighborhood whose shape, size, and influence are still being measured from the inside. To understand where we live, we have to build our address one layer at a time. You are on Earth. Earth circles the Sun. The Sun belongs to the Milky Way, a barred spiral galaxy containing hundreds of billions of stars. The Milky Way belongs to the local group, a small family that includes Andromeda, the Triangulum Galaxy, and dozens of smaller companions. Beyond the local group, galaxies gather into larger structures. The Virgo cluster lies tens of millions of light-years away. Farther still, clusters and filaments form the broad region often called Laniakea, a vast basin of gravitational flow stretching across hundreds of millions of light-years. But even Laniakea is not the full story. Around these dense structures are underdense regions, all connected through the larger architecture of the cosmic web. And the Milky Way may sit deep inside one of them. Astronomers often refer to this broad, underdense neighborhood as the local hole, the local underdensity, or the KBC Void. These names can make the structure sound simple. It is not. There may be no single, perfectly spherical cavity surrounding us. The local universe is shaped by overlapping voids, filaments, galaxy walls, and dense clusters. Depending on which galaxies are counted, which distances are included, and which direction is examined, the underdensity can appear larger, smaller, deeper, or more irregular. That is why different studies sometimes produce different maps. Some suggest a broad region extending for several 100 million light-years around the Milky Way. Others identify a smaller depression nested inside larger structures. Estimates of the missing matter also vary. None of these results should be reduced to one perfect number. The local universe is a complicated landscape. Imagine standing inside an enormous valley at night. The ground beneath you slopes so gently that you cannot feel it. The mountains are too far away to see. Smaller hills and ridges interrupt the valley floor, making it difficult to tell where the lowest point lies. You know the valley exists only because you carefully measure the elevation in every direction. Our situation in space is similar. Galaxies are the landmarks. Their brightness, distance, and motion reveal the shape of the landscape around us. In some directions, galaxies appear more numerous. In others, they are spread more thinly. Their motion suggests that matter is being drawn toward denser structures beyond our immediate neighborhood. The Milky Way is not sitting in complete isolation. The local group still contains many galaxies, and we remain connected to nearby filaments. So the word void must be understood carefully. We are not floating in a perfectly empty bubble. We may be living inside a broad underdensity crossed by smaller structures, like a quiet district within a much larger city. This distinction matters because it changes what the local void can and cannot explain. If the underdensity were extremely deep, perfectly spherical, and centered exactly on the Milky Way, its effect on nearby cosmic expansion could be relatively strong. But the real structure is probably more complicated. We may not be near the exact center. The density may change gradually. One direction may lead toward a nearby wall of galaxies, while another opens into a deeper region of emptiness. This irregularity makes precise predictions difficult and helps explain why scientists continue debating the true boundaries of our cosmic neighborhood. One major challenge is that galaxies do not trace all matter perfectly. Bright galaxies are easier to detect than faint ones. Dust in the Milky Way blocks part of the sky, and no survey sees every direction with equal depth. Even when astronomers count light accurately, light is not the same as mass. A region may contain fewer luminous galaxies without containing exactly the same shortage of dark matter. The relationship between visible galaxies and invisible mass must be modeled, not simply assumed. That is why researchers combine many kinds of evidence. They compare infrared galaxy counts, study supernovae and other distance indicators, measure peculiar velocities, and use gravitational lensing to trace matter that emits no light. Each method offers a different view of the same hidden landscape. And despite the uncertainty, a common picture keeps returning. Our neighborhood appears less dense than many regions farther away. The Milky Way may occupy a cosmic valley broad enough to influence the motions of galaxies over hundreds of millions of light years. This does not make us the center of the universe. There is no evidence that Earth holds any privileged cosmic position. A void can have a center without becoming the center of everything, just as a valley can have a lowest point without becoming the center of a continent. Still, our address may be unusual enough to matter. Astronomy has taught humanity to abandon the idea that we occupy a special place. Earth is not the center of the solar system. The Sun is not the center of the Milky Way. And the Milky Way is not the center of the universe. Those discoveries remain true. But not central does not mean perfectly average. We may live in an ordinary galaxy located inside an unusually thin region of space. And that subtle difference may shape what we observe. When we calculate how fast nearby galaxies recede, their motion includes both universal expansion and local gravitational flow. When we estimate the density of the cosmos, our first sample comes from the neighborhood in which we happen to live. Every observation begins here. That is the deeper importance of the local underdensity. It is not dangerous. It will not swallow the Milky Way. It may never be mapped with one simple boundary. But it reminds us that the universe is always observed from somewhere, and that somewhere has structure. Our instruments sit on a small planet, inside a galaxy, inside a group, inside a web of matter, perhaps near the bottom of an enormous cosmic valley. And valleys do not remain unchanged. Gravity continually draws matter toward denser regions. Galaxies drift. Walls grow heavier. The interior becomes thinner. A valley this large is not standing still. It is evolving. And that is why the hole around us may still be growing. A cosmic void does not grow the way a black hole grows. It does not consume stars. It does not pull galaxies across an invisible edge. And it does not tear new space out of the universe. Its growth is quieter than that. So quiet that, from inside it, nothing seems to happen at all. To understand what is really taking place, imagine a region of space containing slightly less matter than its surroundings. Because it contains less matter, its gravitational pull is weaker. Beyond it, denser filaments, walls, and galaxy clusters exert a stronger attraction. Over billions of years, matter inside the underdense region drifts toward those richer surroundings. Dark matter moves first, shaping the invisible gravitational framework. Gas follows. Galaxies respond to the changing landscape. The interior loses material while the outer boundaries gain it. The void grows not because it swallows the universe, but because the universe continues to empty it. This process began when the universe was young. At first, the difference between the void and its surroundings was almost impossible to notice. The region may have contained only slightly less matter than average. But gravity amplified that small difference. The denser areas attracted more material. The emptier area attracted less. As time passed, the contrast became greater. The surrounding filaments became more massive and more sharply defined, while the interior became increasingly sparse. This is why cosmic voids are not merely empty spaces left behind between galaxies. They are evolving structures. Their walls move, their shapes change, their interiors become thinner, and in many cases, their effective boundaries expand outward. There are two kinds of expansion involved. The first is the general expansion of the universe. On sufficiently large scales, space itself is stretching. Galaxies that are not gravitationally bound become more distant from one another as the universe ages. A void participates in this expansion like every other large region of space. But the second kind of growth is more specific. Underdense regions can expand faster than denser regions around them. In a galaxy cluster, gravity works strongly against cosmic expansion. The galaxies remain bound together. Their mutual attraction can overcome the tendency of space to stretch between them. Inside a void, there is less matter available to resist expansion. Gravity is weaker. The interior, therefore, opens more freely. At the same time, matter near the void's edges is drawn toward surrounding walls and filaments. This creates an outward flow away from the emptiest central region. The combined result is a structure that becomes larger in relation to the denser cosmic web around it. From the perspective of a galaxy inside the void, neighboring galaxies may appear to drift outward, not because the void is pushing them with a new force, not because emptiness has gravity of its own. They move because stronger gravitational attractions lie elsewhere. Imagine a broad, shallow basin with a few loose stones scattered across its floor. Now imagine the land around the basin slowly rising into distant ridges, while the lowest ground becomes flatter and wider. The stones gradually roll toward the slopes. The basin is not pulling them away from its center. The higher surrounding landscape is drawing them outward. A cosmic void evolves in a similar way, although the true process occurs in 3 dimensions and unfolds over billions of years. Its shape may also change as it grows. A void is rarely a perfect sphere. Matter is not distributed evenly around it, so the gravitational pull is stronger in some directions than in others. One side may border a dense galaxy wall. Another may open toward a neighboring underdensity. A thin filament may cross part of the interior. Smaller voids may merge when the boundaries between them weaken. Over time, several separate depressions can become one broader region of emptiness. This is one reason defining the size of our local underdensity is so difficult. There may be no single clean edge. Instead, the Milky Way may lie within a system of connected valleys, each with its own depth and direction, all contributing to a larger flow of matter. Some parts may be actively emptying faster than others. Some boundaries may be moving outward. Others may remain shaped by nearby clusters and filaments. The void is growing, but not like an inflating balloon with a smooth surface. It is more like a changing landscape whose valleys widen while distant ridges gather more material. The rate of this evolution is far too slow to affect daily life. In a human lifetime, the positions of galaxies barely change. Even over the entire history of civilization, the growth of a cosmic void would remain invisible without precise measurements. The Earth stays safely bound to the Sun. The Sun stays inside the Milky Way. The Milky Way and Andromeda remain linked by gravity within the local group. Cosmic expansion does not simply pull apart structures that are already strongly bound. The void's growth acts across vastly larger distances. It reshapes the distribution of galaxies over hundreds of millions of light years, not the orbits of planets or stars. Yet the cumulative effect is enormous. A tiny flow sustained for billions of years can transform a shallow underdensity into one of the largest structures in the cosmos. The emptier the interior becomes, the weaker its gravitational resistance. The more matter collects along the edges, the stronger the surrounding web becomes. And so the contrast continues to grow. Dark energy adds another layer to this story. The universe's expansion is accelerating, driven by something cosmologists call dark energy. Its true nature remains unknown, but on very large scales, its influence causes distant, unbound structures to separate increasingly quickly. Dark energy did not create the first cosmic voids. Their origins lie in early density variations and gravity. But as cosmic expansion accelerates, voids become even more dominant in the volume of the universe. Dense regions remain concentrated in clusters and filaments. The spaces between them continue to widen. The future cosmic web may therefore become more extreme than the one we see today. Matter will be gathered into increasingly isolated islands. Between those islands, enormous regions of darkness will occupy more and more space. Our own underdense neighborhood may be part of that long transformation. It may continue to deepen. Its boundaries may move farther outward. Galaxies near its interior may become more isolated from the dense structures beyond. But predicting its exact future is difficult because we still do not know its precise shape, size, or relationship to surrounding voids. We do know the general direction of cosmic evolution. Matter gathers where gravity is strongest. Emptiness grows where gravity is weakest. The great web becomes more sharply divided between crowded threads and silent interior spaces. And this creates an unexpected consequence. If space inside a void expands slightly differently from space inside a dense region, then observers living in those two places may not measure the same local universe. The laws of physics would remain unchanged. The universe itself would remain one connected reality. But the movement of nearby galaxies, shaped by the local distribution of matter, could look different depending on where the observer stands. And because humanity observes the cosmos from inside this growing underdensity, our measurements may carry the subtle imprint of the whole around us. For nearly a century, astronomers have known that the universe is expanding. The farther away a galaxy is, the faster it generally appears to recede from us. This relationship allows scientists to describe the present expansion rate with a number known as the Hubble constant. In principle, the task seems straightforward. Measure the distance to a galaxy. Measure how quickly it is moving away. Then compare the two. But when astronomers perform this measurement in different ways, the universe gives them different answers. The disagreement is known as the Hubble tension. It is not a dispute over whether space is expanding. Both methods confirm that it is. The mystery lies in exactly how fast the expansion is happening today. One method begins close to home. Astronomers search for objects whose true brightness can be determined. These objects act like lamps of known power, placed at different distances across the universe. Cepheid variable stars are among the first steps. A Cepheid brightens and fades in a steady rhythm. The length of that rhythm reveals how luminous the star truly is. By comparing its true brightness with how faint it appears from Earth, astronomers can estimate its distance. Cepheids then help calibrate Type Ia supernovae. These stellar explosions are visible across far greater distances. Once their brightness is calibrated, they become markers, extending deep into the surrounding universe. This creates the cosmic distance ladder. Geometry helps measure nearby stars. Nearby stars calibrate Cepheids. Cepheids calibrate supernovae. And supernovae reveal how quickly space appears to be expanding across the relatively recent universe. This is our first clock. It is built from stars, explosions, and galaxies we can observe directly. The second clock begins near the opposite end of cosmic history. Instead of looking at nearby stars, it studies the oldest light we can detect. About 380,000 years after the Big Bang, the universe cooled enough for electrons and atomic nuclei to combine. Before then, light was constantly scattered by charged particles and could not travel freely. Once atoms formed, the fog lifted. Light began crossing space. That ancient glow still surrounds us today, although billions of years of expansion have stretched it into microwave wavelengths. We call it the cosmic microwave background. The CMB contains tiny temperature variations, the faint imprints of density differences in the young universe. By studying their size and arrangement, cosmologists estimate the contents and early behavior of the cosmos. They then use the standard cosmological model to calculate how that young universe should have evolved into the one we see now. From this, they infer a present-day expansion rate. This is the second clock. One clock measures the recent universe almost directly. The other begins with the infant universe and predicts the present through a model. If our understanding is complete, the clocks should agree. They do not. The nearby distance ladder generally indicates a faster expansion rate than the rate inferred from the cosmic microwave background under the standard model. The difference is modest in everyday terms, but the measurements are precise enough that it cannot be dismissed as simple rounding. Astronomers tested whether dust, calibration, or telescope limitations might explain it. Yet as Hubble refined the distance ladder and the James Webb Space Telescope examined many of the same markers in infrared light, the broad disagreement persisted. That leaves several possibilities. There may still be an unidentified systematic error. The standard model may be missing something about the early universe. Dark energy may have behaved differently in the past. Unknown particles or fields may have altered the expansion history. Or our local cosmic environment may be influencing the nearby clock. This is where the underdensity around the Milky Way returns to the story. If we live inside a cosmic void, galaxies within and around that region may carry an additional outward motion caused by the surrounding distribution of matter. The local distance ladder would then measure not only the general expansion of the universe, but also a small gravitational flow associated with our underdense neighborhood. To an observer inside the void, nearby space could appear to expand slightly faster than the cosmic average. The idea is elegant because it does not require either clock to be broken. The ancient clock could still describe the average expansion of the wider universe. The nearby clock could still accurately describe what is observed from inside our particular region. The difference would arise because the clocks sample different environments and different eras. But elegance is not evidence. For a local void to explain the entire Hubble tension, it must have the right size, depth, and shape. It must generate enough outward motion without contradicting galaxy counts, direct distance measurements, supernova observations, and the large-scale motions of galaxies. That is a demanding test. Some models find that a local underdensity can reduce the disagreement. Others conclude that the void preferred by current observations is too small or too shallow to remove it completely. The answer also depends on the model. A smooth spherical depression is easier to calculate, but the real local universe contains clusters, filaments, smaller voids, and uneven flows. So the most careful conclusion is not that the local void solves the Hubble tension. It is that the local void may contribute to it. Perhaps it accounts for a modest part of the faster local measurement. Perhaps its influence is larger than some maps suggest. Or perhaps, after every local motion is corrected, most of the tension will remain. In that case, the disagreement would point beyond our neighborhood toward something deeper in cosmology. This is why the Hubble tension matters. It tests whether our best model can connect the early universe to the present without leaving a gap. If the discrepancy comes from measurement, finding the hidden bias will make the distance ladder more reliable. If it comes from local structure, mapping the cosmic web around us will reveal how strongly an observer's address can shape a measurement. And if neither explanation is enough, the universe may be telling us that some part of its history is still missing from our equations. The two clocks are not simply competing numbers. They are two stories of the cosmos. One begins with stars pulsing in nearby galaxies and supernovae flashing in the dark. The other begins with a faint microwave glow, released before any star existed. Both stories travel toward the present, and somewhere along the way, they fail to meet. Our growing cosmic void may occupy part of the space between them. But even if it does not provide the final answer, voids remain valuable for another reason. They are natural laboratories, regions where matter is scarce, gravity is weak, galaxies evolve in isolation, and subtle effects can become easier to detect. Our own neighborhood is only one such experiment written into the cosmic web. Elsewhere, far larger and emptier regions show what the universe becomes when matter has had billions of years to leave. Our local underdensity is not the only great hollow in the cosmic web. Far beyond the Milky Way, astronomers have found regions where galaxies become so sparse that the darkness itself seems to take on structure. One of the most famous is the Boötes Void. It was identified in the early 1980s while astronomers were measuring the redshifts of galaxies in the direction of the constellation Boötes. They expected the map to fill with the usual pattern of groups and clusters. Instead, a broad region appeared with remarkably few galaxies. At first, the emptiness seemed almost too extreme to be real. A gap in the data can come from ordinary causes. Telescopes may miss faint galaxies. Dust can obscure light. A survey may not reach deeply enough. But follow-up observations continue to reveal the same underdense region. The Boötes Void stretches across hundreds of millions of light-years. It is not completely empty. A small population of galaxies exists inside it. Yet compared with the richer cosmic web surrounding it, the region remains extraordinarily sparse. To understand what that would mean for an observer, imagine that the Milky Way had formed much closer to the void's center. The stars within our own galaxy would still fill the night sky. The laws of physics would remain unchanged. But beyond the Milky Way, the darkness would be far more complete. Nearby galaxies that helped astronomers discover the larger universe might not be visible with early telescopes. The idea that the Milky Way was only one galaxy among billions could have taken much longer to establish. A civilization in such a place might spend centuries believing that its galaxy was nearly alone. Only after building instruments powerful enough to see toward the distant edges of the void would it begin to discover the crowded universe beyond. This thought experiment reveals something subtle. The universe does not present every observer with the same evidence. A civilization's location can shape the order in which it discovers reality. Those born near rich clusters would see galaxies everywhere. Those born deep inside emptiness might first encounter a universe that appeared quiet, isolated, and almost complete with only one island of stars. Boötes shows us how a void can limit what is visible. Another vast underdensity may show us how a void can alter the light that passes through it. In one direction of the sky, within the ancient radiation known as the cosmic microwave background, astronomers have identified an unusually cool region called the CMB Cold Spot. The temperature difference is extremely small in ordinary terms, but the cosmic microwave background is remarkably uniform, so even a subtle deviation attracts attention. Along nearly the same line of sight lies a large, underdense region often called the Eridanus Supervoid. This alignment led researchers to ask whether the void might be responsible for at least part of the cold signal. The proposed mechanism is delicate. As ancient light enters a large cosmic structure, gravity changes its energy slightly. In a static universe, the light would gain energy falling in and lose the same amount climbing back out. But the universe is not static. The structure evolves while the light is passing through it. If the light crosses an expanding underdensity, the gravitational landscape can change before the light leaves. The photon may not recover exactly the energy it gained on the way in. By the time it reaches us, it can appear very slightly cooler. This is related to what cosmologists call the integrated Sachs-Wolf effect. The effect is real, but small. Current evidence does not show that the Eridanus Supervoid explains the entire cold spot. The structure may contribute part of the signal, while the remaining anomaly could come from statistical variation, multiple structures along the line of sight, or physics not yet understood. The alignment is worth studying. It is not proof of a complete explanation. And that distinction matters. Cosmic voids invite dramatic language because they are enormous, dark, and difficult to imagine. But their true scientific value comes from subtle effects. They influence how galaxies move. They affect how structures grow. They can weakly alter the light traveling through them. They provide low-density environments where theories of gravity, dark energy, galaxy evolution, and even the mass of elusive particles can be tested. A void is not simply an empty backdrop behind more important objects. It is part of the experiment. Boötes teaches us that emptiness can hide the larger universe from those living within it. Eridanus suggests that emptiness can leave a faint imprint on light older than the stars. And our own local underdensity reminds us that emptiness may also influence the measurements made by observers inside it. 3 different windows, 3 different consequences: visibility, light, motion. Together, they reveal that the least crowded parts of the universe are not passive. They evolve, interact, and preserve a record of how matter has moved across cosmic time. Every great void began as a small shortage of matter. Given enough time, that shortage became a landscape. And the universe is still giving those landscapes room to grow. Cosmic voids are already among the largest structures in the universe, but they are not finished. As the universe continues to expand, the contrast between crowded regions and empty ones will grow more extreme. Matter already bound inside galaxies, groups, and clusters will remain gathered together. Matter that is not bound will become increasingly separated. The filaments of the cosmic web will persist for a time, but the spaces between them will widen. The voids will claim more volume. This does not mean they will consume galaxies like living things. It means the universe will become more divided. Dense islands of matter will remain surrounded by ever larger oceans of emptiness. Our own local group offers a useful example. The Milky Way and Andromeda are gravitationally bound. They are moving toward one another and will eventually interact, merge, and form a much larger galaxy. Nearby smaller galaxies may also become part of that future system. Cosmic expansion will not pull these bound structures apart. Gravity is strong enough here to hold them together. But galaxies far beyond the local group are different. Many are not gravitationally tied to us. As accelerated expansion continues, they will recede faster and faster. Their light will become more strongly redshifted, stretched into longer and weaker wavelengths. Over immense periods of time, they will become harder to see. Then, they will disappear beyond the cosmic horizon, not because they cease to exist. They will vanish because the space between us and them expands so quickly that new light from those galaxies will never reach us. The observable universe of the distant future will therefore appear smaller, even while the universe itself continues to grow. For a civilization living then, the sky may reveal only one large, merged galaxy surrounded by darkness. The cosmic web visible to us today may no longer be observable. The great voids will no longer appear as empty spaces between visible structures, because the structures themselves will have disappeared from view. Emptiness will seem complete. Imagine astronomers arising on a planet hundreds of billions of years from now. They build telescopes and map the large galaxy surrounding them. But when they look beyond it, they find almost nothing. No nearby spiral galaxies. No rich clusters in the distance. No broad web of matter stretching across the sky. They may have no obvious evidence that other galaxies ever existed. Their universe could appear calm, dark, and almost static. This would not mean they were less intelligent than us. They would simply be living at a different time. Just as location shapes what an observer can discover, cosmic age shapes what evidence remains available. Today, we can detect the cosmic microwave background, the ancient glow released when the universe first became transparent. But that light is also being stretched by expansion. As time passes, its wavelength grows longer and its temperature falls. In the far future, it may become so faint and deeply redshifted that even advanced instruments struggle to distinguish it from other sources. The oldest visible record of the Big Bang could effectively disappear. The universe may slowly erase the evidence of its own beginning. Future astronomers could still study stars and black holes, but reconstructing the larger history of the cosmos might become almost impossible. Without distant galaxies, they could not easily discover universal expansion. Without the cosmic microwave background, they would lose one of the clearest windows into the early universe. Without visible clusters and filaments, they might never infer the cosmic web. They could live inside an enormous void without realizing that the darkness around them was only one part of a much larger structure. This possibility gives our era a special importance. We live at a time when the universe is old enough for galaxies, planets, and observers to exist, but still young enough for the large-scale cosmos to remain visible. The ancient light can still be measured. Distant galaxies can still be detected. The expansion of space can still be traced across billions of light-years, and cosmic voids can still be recognized as regions within a greater web. We are not living at the center of cosmic history, but we may be living during one of the few eras when that history can be read. The future evolution of our local underdensity remains uncertain in detail. The local group's future will be shaped more by the Milky Way, Andromeda, and their surrounding dark matter than by the void itself. Yet the larger direction is clear. Unbound structures will separate. Voids will occupy an increasing share of the universe's volume. Dense regions will become isolated islands, and the distance between those islands will grow. This is not a violent ending. There is no single moment when the lights go out. The transformation happens slowly, across timescales longer than the current age of the universe. One distant galaxy fades, then another. Clusters become dim points. The points slip beyond reach. The web dissolves from view. And silence fills the distance between the remaining islands of matter. The universe of the far future may be emptier, not only in structure, but also in knowledge. Its inhabitants may look into darkness and see no trace of the connected cosmos that once surrounded them. But tonight, that cosmos is still here. The galaxies still line the filaments. The ancient light still crosses space. The voids still reveal their boundaries through the motion and absence of matter. And from our unusual cosmic address, we can still watch the universe before its largest structures fade beyond sight. We live inside a growing emptiness, yet we also live during the brief age when that emptiness can still be understood. And now, after traveling across billions of light years and billions of years, return for a moment to where you began. Back to the room around you, back to the quiet air, back to the familiar weight of the earth beneath you. Nothing here appears changed. There is no sign in the ceiling above you that our galaxy may lie inside an enormous underdensity. No line across the night sky marks the boundary of the local void. No sound reaches us from the distant walls where matter gathers along the cosmic web. The process is too large, too slow, and too quiet for human senses. Yet it continues. Far beyond the solar system, galaxies move through a landscape shaped by gravity. Some drift toward clusters, others follow the long paths of filaments. Matter gathers where the cosmic web is strongest, while the interiors of voids gradually become thinner. The hole around us is not opening beneath the Earth. It is not pulling the Milky Way into danger. It is a change unfolding across distances so immense that a beam of light could travel for hundreds of millions of years without crossing them. On those scales, our entire galaxy is little more than a spark. And still, from that spark, we have begun to map the darkness. We have learned that the universe is not filled evenly with galaxies. It has valleys and ridges. It has crowded intersections where thousands of galaxies gather, and vast interiors where matter has slowly drained away. We have learned that emptiness is not the absence of history. A void carries the memory of the early universe. Its shape reveals where matter once rested, where gravity drew it, and how tiny differences grew over billions of years into the largest structures we know. And we have learned that our own view is never completely separate from our location. Every telescope looks outward from one planet. Every measurement begins inside one galaxy. Every attempt to understand the universe is made from somewhere within the structure being measured. Our maps are extraordinarily successful. They can trace galaxies across enormous distances. They can detect light released before the first stars formed. They can estimate how quickly space is expanding and reconstruct conditions from the earliest eras of cosmic history. But the map is still being drawn from inside the landscape. That is what makes the local underdensity so important. Not because it proves that everything we know is wrong, not because it places Earth at the center of anything, but because it reminds us that even our cosmic neighborhood can leave a subtle imprint on the questions we ask and the answers we measure. Perhaps the void contributes slightly to the disagreement between the two clocks of cosmic expansion. Perhaps future surveys will show that its influence is smaller than we thought. Perhaps its true boundary will turn out to be irregular, broken into several connected valleys, rather than one enormous sphere. Science does not lose its wonder when uncertainty remains. The uncertainty is where the next discovery begins. Somewhere tonight, astronomers are measuring the distances to galaxies. Others are tracing their motions. Some are studying the faint bending of light through regions where matter is scarce. Piece by piece, they are reconstructing a structure too large for any observer to see directly. And each new measurement slightly sharpens our position within the web. In the distant future, much of that web may disappear from view. Galaxies beyond our gravitational neighborhood will fade beyond the horizon. The ancient background light will stretch into wavelengths almost impossible to detect. Future observers may look outward and find only darkness beyond their own island of stars. But we do not live in that silent age. We live while the evidence is still visible. The distant galaxies still send us their light. The cosmic microwave background still surrounds us. The web can still be mapped, and the voids can still be recognized as the enormous, evolving spaces between the luminous structures of the universe. For a brief period in cosmic history, the universe is able to look back at itself through us. Through telescopes built on a small world, through instruments placed above the atmosphere, through minds capable of noticing that entire regions of space contain less than they should. Perhaps that is the quietest truth in this story. We are surrounded by emptiness, yet we are not separated from the universe. The atoms in your body were created inside stars. The Earth formed from material gathered by gravity. The Milky Way grew along the same cosmic web that shaped the void around it. Even here, inside a region defined by what it lacks, everything remains connected to the history of everything else. So imagine rising once more above the room, above the sleeping cities, above the clouds and the blue edge of Earth. The moon becomes a pale point below you. The planets slip quietly into the distance. The sun joins the other stars of the Milky Way, and the galaxy slowly reveals its spiral shape. Continue outward. The Milky Way becomes one light among the galaxies of the local group. The local group becomes a small knot within a much larger flow. Farther still, clusters align into filaments. Filaments stretch into walls, and between them open the great dark interiors of the cosmic web. Somewhere within that immense structure is our home. A small galaxy inside a broad cosmic valley, not at the center of the universe, not outside its laws, simply located in one particular place, looking outward, trying to understand the whole. You are not falling into the hole. You have always been inside it. And while galaxies rest along the distant threads of the cosmic web, the emptiness between them continues, almost imperceptibly, to grow.